Section E5 of astrophysics is stellar processes and stellar evolution. We're going to look at stellar processes to start with. Nucleosynthesis. How does a star start? The conditions that are needed to initiate fusion in a star. I have a short flash movie that I have managed to find, which I will show you. So, the formation of stars. They're formed from giant clouds, for example, Orion Nebula. Dust clouds, under their mutual gravitation, will start to collapse and condense. So we have a temperature of about 100 Kelvin, which is pretty cold, with 10 to the 10 or 10 to the 19 particles. Most of it, of course, is hydrogen with some helium and stellar dust. So, due to this gravitational attraction and this high density, this volume contracts. As the gravitational potential energy turns into kinetic energy, the temperature rises. So eventually it ionizes and then nuclear fusion. If the temperature and the pressures are high enough, you get nuclear fusion. And then at that point where main sequence stars are shown as soon as hydrogen is fused into helium, that is the main sequence star, when it basically kicks off, when it ignites. We have this stability between the radiation pressure and the gravitational pressure, which supports the weight of the star. Here we have a photo which shows, for example, this dust cloud. There's a big gap here. This was full of dust. This is all, by its mutual gravitation, collapsed to make this protostar here. Here, the protostar is so dark that we're not seeing it yet, but it is forming at this point here. Here we can see a fairly well-developed star here. Because it's a large gas cloud which is collapsing, we have a huge surface area. So even though it's quite cool, it's going to be very bright because it's got such a large surface area, which means it's going to be very luminous. This is the formation of the dust cloud. It moves along this path as it collapses, and then starts to burn here at point 2. So basically 3 is when the formation of a star. With the protostar, where this gas cloud is starting to collapse, then it starts to heat up and will start to glow because it becomes so hot. And then it lands on the main sequence at whatever point it is here, and then it will start to fuse. So where the protostar lands on the main sequence is determined by its initial mass. If it's a very small mass star, it will land here. If it's large, it will land here. It depends how big the cloud of gas is. So if you have a star of roughly 15 solar masses, it will take 10,000 years. If it's 1 solar mass, then it will take about 7 years for it to form and land on the main sequence. So this is the path showing the time taken to land on parts of the main sequence. What are the upper and lower limits? So the gravitational collapse puts a lower and upper limit on the mass of the matter. If it's a protostar of less than 10% of a solar mass, there is not enough temperature and pressure for it to start fusing, and it will glow, but it will not fuse. It's not really a star. It will be a brown dwarf. If we have a mass which is greater than 100 solar masses, the internal pressure is greater than the gravitational pressure. So vast amounts of matter will be ejected because of this pressure. And therefore it's going to disrupt the evolution of the star. So stars cannot exist that are greater than 100 solar masses because they would be too unstable to form.